Welcome to the fascinating world of wave optics. In this video, we'll explore how light behaves not just as a particle, but as a wave. This branch of physics helps us understand phenomena like interference, diffraction, and polarization, effects that can't be explained by simple ray optics. Wave optics, also known as physical optics, dives deeper into the nature of light, revealing its mysterious and beautiful behaviors. Throughout this journey, we'll see how everyday observations, from the colors on a soap bubble to the patterns created by a CD, are all rooted in the wave nature of light. Let's begin our exploration by understanding what sets wave optics apart from geometric optics. For centuries, scientists debated whether light was a wave or a particle. Isaac Newton believed light was made of particles, while Christian Huygens argued it was a wave. Today, we know light exhibits both behaviors, but wave optics focuses on its wave-like properties. This duality is crucial for understanding phenomena like interference and diffraction, which cannot be explained by particle theory alone. As we move forward, keep in mind that the wave model of light opens up a new perspective on how we perceive the world around us. Before diving deeper, let's clarify what a wave is. A wave is a disturbance that transfers energy from one place to another without transferring matter. In the context of light, we're dealing with electromagnetic waves, oscillating electric and magnetic fields that travel through space. These waves have properties like wavelength, frequency, and amplitude, which determine their color and intensity. Understanding these basics is essential for grasping the more complex behaviors we'll encounter in wave optics. Wavelength is the distance between two consecutive peaks of a wave, while frequency is the number of waves passing a point per second. In light, different wavelengths correspond to different colors. For example, red light has a longer wavelength than blue light. Frequency and wavelength are inversely related. When one increases, the other decreases. These properties are fundamental in understanding how light interacts with objects and creates the beautiful patterns we see in wave optics. Amplitude refers to the height of a wave from its central axis. In light waves, amplitude is related to brightness or intensity. The greater the amplitude, the brighter the light appears. Intensity is the amount of energy a wave carries per unit area. These concepts help explain why some light sources appear brighter than others, even if they emit the same color. As we explore interference and diffraction, amplitude and intensity will play important roles in the patterns we observe. Principle of superposition states that when two or more waves overlap, the resulting wave is the sum of the individual waves. This principle is at the heart of many wave optics phenomena such as interference and diffraction. When light waves meet, they can reinforce each other, creating brighter regions, or cancel each other out, resulting in darkness. This simple yet powerful idea explains much of the complexity we see in wave-based behavior. Interference occurs when two or more light waves overlap. If the waves are in phase, their amplitudes add up, creating bright spots. This is constructive interference. If they're out of phase, their amplitudes subtract, leading to dark spots. This is destructive interference. The beautiful patterns formed by overlapping waves are a direct result of this phenomenon. Interference is a key concept in wave optics, helping us understand everything from soap bubbles to advanced scientific instruments. One of the most famous demonstrations of wave optics is Young's double-slit experiment. In this experiment, light passes through two narrow slits and creates an interference pattern of bright and dark bands on a screen. This pattern can only be explained if light behaves as a wave, with the waves from each slit reinforcing or canceling each other. Young's experiment provided strong evidence for the wave theory of light and remains a cornerstone of physics education. Have you ever noticed the colorful patterns on a soap bubble or an oil slick? These are caused by thin film interference. When light reflects off the top and bottom surfaces of a thin film, the waves can interfere constructively or destructively, depending on the film's thickness and the wavelength of light. This creates the vivid colors we see. Thin film interference is a beautiful everyday example of wave optics in action. Diffraction is the bending of light as it passes around obstacles or through narrow openings. Unlike geometric optics, which predicts sharp shadows, wave optics shows that light can spread out and create patterns of light and dark. Diffraction is most noticeable when the size of the obstacle or opening is similar to the wavelength of light. This phenomenon is essential for understanding how light behaves in real-world situations. When light passes through a single narrow slit, it spreads out and forms a pattern of bright and dark bands on a screen. This is called single-slit diffraction. The central bright band is the widest, with dimmer bands on either side. The pattern results from the interference of light waves emerging from different parts of the slit. Single-slit diffraction demonstrates how even a single opening can reveal the wave nature of light. Diffraction grating is an optical device with many closely spaced slits. When light passes through or reflects off the grating, it produces a series of sharp, colorful lines. These patterns are much more detailed than those from a single or double slit. Diffraction gratings are widely used in scientific instruments to analyze the spectrum of light, helping us understand the composition of stars and other distant objects. Polarization refers to the orientation of light's electric field. Unpolarized light vibrates in all directions, while polarized light vibrates in just one direction. Polarization can occur through reflection, scattering, or by passing light through special filters. Polarized sunglasses, for example, block certain orientations of light to reduce glare. Understanding polarization is important in many technologies, from photography to LCD screens. Alice's law describes how the intensity of polarized light changes as it passes through a polarizing filter. The intensity depends on the angle between the light's polarization direction and the filter's axis. When the angle is zero, maximum light passes through. As the angle increases, the intensity decreases, reaching zero when the directions are perpendicular. This law helps us design devices that control light's brightness and polarization. Polarization has many practical uses. In photography, polarizing filters enhance contrast and reduce reflections. In 3D movies, different polarizations are used for each eye to create a sense of depth. Polarization is also crucial in LCD screens, optical communication, and even in studying stress patterns in transparent materials. These applications show how wave optics principles are woven into modern technology. Coherence describes how well the phases of light waves match over time and space. Coherent light, like that from a laser, has waves that are in step with each other, producing clear interference patterns. Incoherent light, like sunlight, has random phases and does not create stable patterns. Coherence is essential for many wave optics experiments and technologies, such as holography and fiber optics. There are two types of coherence: temporal and spatial. Temporal coherence refers to how consistent the phase of a wave is over time, while spatial coherence refers to how consistent it is across different points in space. Lasers are highly coherent in both senses, making them ideal for precise experiments. Understanding these types of coherence helps us design better optical systems and interpret interference patterns. Huygens' principle states that every point on a wavefront acts as a source of new wavelets. These wavelets spread out in all directions, and the new wavefront is the envelope of these secondary waves. This principle explains how waves propagate, bend around obstacles, and form diffraction patterns. Huygens' principle is a foundational idea in wave optics, helping us visualize and predict the behavior of light. Wavefront is a surface over which the phase of a wave is constant. Rays are lines perpendicular to the wavefront, showing the direction of energy flow. In wave optics, we focus on wavefronts to understand how light spreads and bends, while in geometric optics, we use rays for simpler calculations. Recognizing the difference helps us choose the right model for different situations. Diffraction can be classified into Fresnel and Fraunhofer types. Fresnel diffraction occurs when the light source or screen is close to the obstacle, resulting in complex patterns. Fraunhofer diffraction happens when both are far away, producing simpler, well-defined patterns. Understanding the difference helps us analyze and predict the results of various optical experiments. Diffraction isn't just a laboratory phenomenon, it's all around us. The colorful patterns on CDs and DVDs, the spreading of sound around corners, and even the blurry edges of shadows are all examples of diffraction. Recognizing these effects in daily life helps us appreciate the wave nature of light and sound, connecting physics to our everyday experiences. Nature is full of interference effects. The iridescent colors of peacock feathers, butterfly wings, and oil films are all caused by the interference of light waves. These natural displays are not only beautiful but also demonstrate the principles of wave optics at work in the world around us. Observing these patterns can inspire curiosity and wonder about the science behind them. Michelson interferometer is a device that splits a beam of light in two paths, then recombines them to create interference patterns. By analyzing these patterns, scientists can measure tiny distances with incredible precision. This instrument has been used in groundbreaking experiments, including the detection of gravitational waves. The Michelson interferometer showcases the power of wave optics in scientific discovery. Newton's rings are circular interference patterns formed when a convex lens is placed on a flat glass surface. The varying thickness of the air film between the surfaces causes constructive and destructive interference, creating a series of bright and dark rings. This phenomenon is a classic example of wave optics and is used to measure the flatness of surfaces and the wavelength of light. Birefringence is a property of certain materials that split light into two rays, each polarized at a different angle. This occurs because the material has different refractive indices along different axes. Birefringence is used in stress analysis, mineral identification, and creating special optical devices. It's another fascinating outcome of the wave nature of light. Optical path difference refers to the difference in distance traveled by two light waves before they combine. This difference determines whether the waves interfere constructively or destructively. By controlling the optical path difference, we can create and manipulate interference patterns, which is essential in many optical instruments and experiments. Phase difference is the amount by which one wave is ahead or behind another. It's measured in degrees or radians. The phase difference between two light waves determines how they interfere, whether they reinforce or cancel each other. Understanding phase difference is crucial for predicting and analyzing interference and diffraction patterns. Wave optics principles are vital in modern communication technologies. Fiber optic cables use the wave nature of light to transmit data over long distances with minimal loss. Interference and diffraction are used in designing optical filters and multiplexers, which allow multiple signals to travel through a single fiber. These advances have revolutionized how we share information globally. Lasers produce highly coherent, monochromatic light, making them ideal for many applications. The coherence of laser light allows for precise interference and diffraction experiments, holography, and even medical procedures. Lasers are a direct application of wave optics, demonstrating the power of controlling light's wave properties. Holography is a technique that records and reconstructs the full wavefront of light, creating three-dimensional images. It relies on the interference of coherent light, usually from a laser. Holograms store both the intensity and phase information of light, allowing for realistic 3D visuals. This technology is used in security, data storage, and art. Many optical instruments rely on wave optics principles. Microscopes, telescopes, and spectrometers use interference and diffraction to enhance image quality and analyze light. Understanding wave optics allows engineers to design better lenses, filters, and detectors, pushing the boundaries of what we can observe and measure. Resolution of an optical instrument is limited by diffraction. Even with perfect lenses, the wave nature of light causes images to blur beyond a certain point. This is known as the diffraction limit. Understanding this limit helps scientists and engineers develop techniques to overcome it, such as using shorter wavelengths or computational methods. Fiber optics use the wave nature of light to transmit information over long distances. Light travels through thin glass fibers by total internal reflection, maintaining its intensity and coherence. Fiber optics have revolutionized telecommunications, enabling high-speed internet, cable TV, and medical imaging. This technology is a direct application of wave optics in our daily lives. Rainbow colors you see on CDs and DVDs are caused by diffraction. The tiny grooves on the disc act as a diffraction grating, splitting white light into its component colors. This everyday example shows how wave optics principles are embedded in technology and entertainment, creating beautiful effects we often take for granted. Anti-reflection coatings on glasses and camera lenses use thin film interference to reduce unwanted reflections. By carefully choosing the thickness and material of the coating, destructive interference cancels out reflected light, making lenses clearer and more effective. This is another practical application of wave optics in everyday products. Any vibrant colors in nature, like those on butterfly wings and peacock feathers, are not due to pigments but to structural color. This effect arises from microscopic structures that cause interference and diffraction of light. Structural color is a stunning demonstration of wave optics in the natural world, producing iridescent and shifting hues. Rainbows are a familiar sight, but their formation involves more than just refraction. Wave optics explains the supernumerary bands, faint, extra arcs inside the main rainbow caused by interference of light waves within water droplets. This adds another layer of beauty and complexity to one of nature's most captivating displays. X-ray diffraction is a technique used to study the structure of crystals. When X-rays pass through a crystal, they are diffracted in specific directions, creating a pattern that reveals the arrangement of atoms. This method has been crucial in discovering the structures of DNA, proteins, and many other materials, showcasing the power of wave optics in scientific research. While wave optics explains many phenomena, light also has quantum properties. Photons, the particles of light, can interfere and diffract just like waves. Quantum optics combines wave and particle models, leading to new technologies like quantum communication and computing. This intersection of wave and quantum physics is a frontier of modern science. Astronomers use wave optics to study distant stars and galaxies. Interference and diffraction help analyze starlight, revealing information about composition, motion, and distance. Advanced telescopes use adaptive optics and interferometry to overcome the limits set by diffraction, allowing us to see deeper into the universe than ever before. Medical imaging technologies such as optical coherence tomography and laser surgery rely on wave optics. These techniques use interference and diffraction to create detailed images of tissues or to perform precise surgical procedures. Wave optics has transformed medicine, making diagnosis and treatment safer and more effective. Artists and designers use wave optics to create stunning visual effects. Holography, iridescent paints, and optical illusions all rely on interference and diffraction. By understanding the science behind these effects, creators can craft experiences that captivate and inspire, blending art and physics in unique ways. Wave optics can be challenging to study and apply. The mathematics can be complex, and real-world conditions often introduce complications. However, advances in technology and computation are making it easier to model and harness wave optics for new applications. Embracing these challenges leads to innovation and discovery. Future of wave optics is bright. New materials like metamaterials are enabling unprecedented control over light. Quantum optics is opening doors to secure communication and powerful computers. As we continue to explore the wave nature of light, we'll unlock new technologies and deepen our understanding of the universe. Summary: wave optics reveals the rich and complex behaviors of light that go far beyond simple reflection and refraction. From interference and diffraction to polarization and coherence, these phenomena shape our world and drive technological progress. By understanding wave optics, we gain new insights into nature, technology, and the universe itself. Thank you for joining this journey into the wonders of wave optics.